Okay, everyone, welcome back. So this is a group problem, and you're probably sitting at home. To help you out, try finding the nearest squirrel and asking it to assist you in this problem. If you don't speak squirrel, well, that's on you. You should always pick up a second language. Now, moving on. So, what's the problem asking us to do? Well, we've got a beam. Luckily, it's a symmetric beam. I love symmetry because we know exactly where the centroid is. And it says if the bending stress at point K is 35 megapascals in tension, determine the bending stress at point H, and state whether the normal stress at H is tension or compression. Also, if the allowable bending stress is going to be 165 megapascals, determine the magnitude of the maximum bending moment that can be supported by the beam. Okay, maximum bending moment supported by this beam. With that, let's jump straight into it. Wait, what am I doing? No, you're going to start this problem on your own. You're going to try it on your own. I know you can do it. You and that squirrel's a smart squirrel, I'm sure of it. So, you work together and see how it goes. Okay, so 3, 2, 1, and you're back. Okay, so let's try it out together. First thing we need to do is figure out what the moment of inertia is going to be. Now, sadly, even though it's nice and centered, when we're calculating moment of inertia, these are not centered on the centroid. The centered one is. Oh my god, it's centered on the centroid. It's like a tongue twister. And we're getting some big numbers because this is all in millimeters to the fourth. So first what we do is we calculate the moment of inertia about their own centroid, which since they're all rectangles, it's 1/12 base height cubed. And so the web is much taller than all the rest, and so it has a much larger moment of inertia. While these do not. They have a very small height. But then we have to take into account the fact that their distance from the centroid is quite great. They're 160 millimeters from the center to their centroid, which is right in the middle of the box. So we then have to have that correcting term from our parallel axis theorem, which is d squared a, which is 184 million millimeters to the fourth. So in the end, these top two sections actually are our biggest contributors to the moment of inertia, even though initially they were practically nothing. So parallel axis theorem, it is definitely important. And this gives us our moment of inertia, which is 402 million. Okay, now at point K, we know what y is. It's negative 90 millimeters. We moved down from the centroid. And at point H, y is equal to negative 175 millimeters. And this is going to be kind of a glorious thing here. So we know that the bending stress at K is 35 megapascals. Also, the bending stress varies linearly. It's like similar triangles. So you don't actually have to do any calculations here. You don't have to calculate the bending moment at all. All you have to do is realize that you have some sort of little triangle here. It's two similar triangles. This is 90, and this distance right here is 175. That's 35, and so the ratio should be the same. So we have 90 over 35. Sorry, 90. Oh goodness, I'm mixing it all up. 35 over 90 right here. And over here we have 175, and we don't know what that stress is, so it'll be x. And we plug everything in and solve. What we get is it's going to be 68.1 megapascals. 68.1 megapascals. Okay, so what's the next one? Well, we want to find that maximum internal bending moment so that we don't go over our maximum bending stress. Well, luckily for us, this is a completely symmetric member, which means we know that the distance to where we're going to have a maximum stress is going to be 175 millimeters. It's just the distance from the center all the way to the top, so half the height. We have our maximum bending stress right here, which is 165 megapascals, which is also the same as Newton per millimeter squared. And we know what our moment of inertia is from earlier. So if we plug all this in, we have our answer. Our maximum bending moment is going to be 379 million Newton millimeters, or we can say 379 kilonewton meters. So depending on how you want to move it around. And that's it. That, I think, is everything it asked us for. Let me see. Yes, it is. So we are done with this problem. What did we do? Well, we used our flexure formula to calculate the maximum bending moment. It's kind of doing things a little differently than the last time. We used similar triangles to calculate a stress at a second point given 1 point. And we used our basic equations for moment inertia to calculate the moment inertia for this section. So thank you for listening. I hope this helps you, and I'll see you all next time. Have a wonderful day. Bye-bye.